Greetings, students. Today we're going to discuss 2.4. So we're going to discuss, first thing we're going to discuss is the basic functions, the 12 basic functions. We're going to do domain, range, increasing, decreasing, symmetry, and then asymptotes. So there's a lot of things to talk about here. So for domain, we're going to call this D. And we're going to talk about this for all the functions first. And then we're going to come back and then we're going to do the range for all of the functions. So D. So domain is the values that x can possibly be. So are there limits to x? So what this means is, with domain is, are there possible values of x that you cannot use? Are there values of x we can't use? In other words, is there some number, some real number that you cannot substitute in for x to receive a y value? So we're looking at the first function here. For any value of x, we will receive a y value. So regardless if x is negative, positive, 0, anything can be substituted in for x here. So for example, if we put in x equals 4, we get y equals 4. If we put in x equals negative 6, we get y equals negative 6. That's what we mean. Are there values of x that we can't use? No. So what that means is that our domain is infinite. We write that in our notation, our set notation here. Negative infinity, comma infinity. In other words, our domain is not limited on this function. For the second function, the same thing applies. We can substitute in a 2 for x and we get a 4 for y, a negative 2 for x, we get a 4 for y. Substitute a 0 for x, we get a 0 for y. Now it doesn't matter if we substitute the same value of x in, or a different value of x, sorry, and get the same value for y. For example, if we substitute 2 or negative 2 in for x, we get the same y value for. That's not what this is talking about. It's talking about, are there values of x that we can't use? In other words, are there values of x that cannot be substituted in? And the answer to that is no again. So negative infinity, comma infinity. The third one has a similar vibe to it. For every value of x, we can put in any value of x. There exists a value for y. And again, these values of y do not have to be unique. But for every value of x here, there exists a value of y. So if we substitute 1 in for x, we get 1 out for y, negative 1, 2, we get 8 out, negative 2, we get negative 8 out. So once again, our domain is infinite here. Question 4 is the first one, the first example where our domain is not infinite, where there are values of x that we can't use, where there are values of x that cannot be substituted in. So I'm looking at question 4 here. What values of x cannot be substituted into this equation? The answer to that question is negative values. Now I know when we substitute negative values in, they will yield complex numbers. But complex numbers do not graph on a real number coordinate plane. This is a real plane, not a complex plane. It does not have I in it. So in other words, I can substitute 0 in for x and get 0 out for y. But anything less than 0 cannot be substituted in for x. Therefore, my domain starts at 0 and goes up. That's what this means here. We go from 0 up. And I shouldn't say up, I should actually say to the right. From 0 to the right. Because domain is the x values. So from 0 to the right, those are the x values that we can use. We can't use anything left of 0 for my x values. A similar thing happens here with the natural logarithm. The only difference here is that you cannot substitute 0 into a natural logarithm. The ln of 0 does not exist. And we talked about that in the past because you can't have e to a number equal to 0. So we cannot have that working. So this will be the same, except it will have a parenthesis instead of a bracket. Open instead of closed, if you want to call it that. 0, comma infinity. In other words, everything right of 0, not including 0 here. And then on this one, everything right of 0, including 0. Alright, question 6 kind of got stuck onto 2 different pages. So here is the graph of it. I'm asking you for the domain here though. So on the reciprocal function, every value of x works that's left of 0 and right of 0, but 0 does not, because division by 0 is not appropriate and does not work. So we're going to say x cannot equal 0 here. If you want to write it a different way, you could say negative infinity, comma 0, union 0, comma infinity. What that means is x can be anything but 0 on this particular equation or function. Okay, the exponential function. So here again we're looking at the values of x. I can substitute a value in for x and it will yield a value for y every time. So if x is negative, it's going to yield a fractional answer. So for example, if x was negative 1, this would be 1 over e. E is a number, the natural number. If x was negative 2, it would be 2. It would be 1 over e squared, sorry. If x was negative 3, it would be 1 over e to the third. Similarly, we can substitute in larger values of x as well. E squared, e to the third, e to the fourth. So my domain here is not limited. My domain will be negative infinity, comma infinity. As we can substitute any value in for x here as well. On number 8, we have a similar vibe happening. The domain can be any number, any real number, as we can substitute in negative values and positive values for x. On number, sorry, this is number 9, that one's number 8. Number 9 now, the real number 9. Again, the domain is not limited. When we see a limited domain, what should happen is the graph should either have a value that it's not got an output for, like this one, the 1 over x, number 6, or it should have a cutoff to the left or to the right. So this one doesn't go left of 0, and this one doesn't go left of 0. So when you're seeing a domain limitation, you should see some sort of cutoff to the left or to the right, or you should see a value that doesn't have an output. Alright, this one, same deal. The domain is not limited by anything. So negative infinity, comma infinity. This one, same thing as well. Now, this one's kind of an odd. The greatest integer function is kind of a weird function. What it does is it rounds things up. I should say rounds them down. So from anything from 0 to 1, your output is 0. For any x value from 0 to 1, your output is 0. For any x value from 1 to 2, your output is 1. For any x value from 2 to 3, your output is 2. So it's rounding basically the y value down. I should say not the y value. It's rounding the x value down to be the y value. And it's not really rounding, it's just putting it always down. So anyways, so an x value of 1.9 would yield a 1 for the y value, in other words. But we can use any x value here. The domain is not limited. There is no limitation in the domain on this particular function. And I did say for 12, so there obviously is one on the back, which is this one. 1 plus e to the negative x. So we can put any x value into this. It does have it graphed for us nicely. We can see the graph here. Any x value can be substituted into this particular function. So my domain, negative infinity, comma infinity. Alright, so there's all 12 domains. Let's go back down, let's talk about range. So now I'm going to talk about all the ranges here. So the range is the same thing as domain, except it's going to ask about are the y values. Are there any values of y we can't use? So whereas the domain is any values of x, the range is any values of y. So this particular range R, is unlimited. In other words, we have all the y values. Now if we're looking at question 2 next, notice how it cuts off at y equals 0. There's nothing below 0 for the y values. That's what we're going to call a limited range. In other words, the range is limited. It's not going, the y values don't go below 0. So here, we can attain a value of 0, but we can't attain a value less than 0 for the y values. In other words, we don't have any y's less than 0. So that's what you should see with a limited range. You should see a cutoff in the y values. In other words, we can't have below 0 here in the y values. This one, we can have every y value. So this is unlimited range. Negative infinity, comma infinity. This one, once again, we can't attain a value below 0 for the y values. So we have a limited range here. We could attain a value of 0 if x was 0, but we can't attain a value less than 0. Okay, question 5. This one is a little confusing every year for students. Notice how ln of x, when x is a fractional, it gets more and more negative for the y values. So this graph does in fact point downwards and upwards. In other words, we can attain every y value here. So the range here is actually unlimited. All values. Alright, looking at this next one, the reciprocal function. We can't have this be equal to 0 because you can't substitute a value in for x to make this 0, this fraction 0. So this will have a limited range. Y cannot be 0. So y will never equal 0 here, which you can also write similarly to this one here. In fact, the exact same way. So negative infinity, comma 0, union 0, comma infinity. Alright, question 7, the exponential function. Notice again how this is limited. It does not go below the y-axis. So this has a limited range. Now will it ever actually equal 0, the y value is the question. So we're asking ourselves, does this actually equal 0 ever? No, no matter what x I put in, no matter how negative x is, negative 10, negative 20, negative 30, this will never be equal to 0. It will get closer and closer to 0. In fact, it'll get infinitely close to 0. We'll talk about that in the next items, the asymptotes. But we'll never actually attain 0. So this range is from 0 and up. This range, notice how it's a wave. It goes up and down, up and down. The y is never above 1 and never below negative 1. So y is always between 1 and negative 1, the outputs, in other words, the possible y values. So we're going to write that as closed brackets. In other words, the function exists between negative 1 and 1. The y values exist between negative 1 and 1. There's nothing above positive 1. There's nothing below negative 1 for the y values. And the same thing applies with the cosine function. The function exists between negative 1 and 1. The largest y value is negative 1. The smallest y value, the largest y value is positive 1. And the smallest y value is negative 1. Here we have a limitation. Y is never negative here. So y is always positive. 0, comma infinity. And here we have a weird function going on. Y is never a fraction. Y is always an integer. So from my range here, now this is not the proper way to write the range by any means, but for the range here, I'm just going to put y is never, should not use the word never, always an integer. In other words, y can't be fractional, it can't be a square root, that's not an integer square root, or not a perfect square in other words. And it's not, so it's never fractional, and it can't be anything other than an integer. So y is 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. And in terms of writing that like this, you would have a large notations, you would have a parenthesis, you would have, for the range, you'd have parenthesis 1, comma 2, comma 3, comma 4, comma 5, dot, 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 dot. And you'd have the negative as well on these sides. So you'd actually have dot, 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 negative 1, negative 0, 1, 2, dot, dot, dot. Or you could just say integers, all real integers, or all integers. Be able to say that. All right, for this one, we have this graph for a reason. So the y values here exist between 0 and 1. That's my range. The y values exist between 0 and 1, non-inclusive. Okay. Next up, decreasing and increasing. So let me do this one in green. So as we look from left to right, is it decreasing or increasing? So when you're doing decreasing and increasing, it goes from left to right. From left to right. And decreasing, it means the y is going down in value. Increasing, it means it's coming up. So on this particular function is always increasing. Now a line going the other way would always be decreasing. Why? Because if you take a value on the left and you go towards the right value is larger, the y value for it, than the left value. So we're talking about x's and y's here. So with the x value on the left, look at its y value. So example here, x is -6, y is -6. Compare that with the x value next to it, to the right of it. When x is -5, you can see y has increased by 1. So this one's increasing, only increasing. So we don't have to specify here, we can just say increasing. It's always increasing. Now this one, notice how on the left here, when we take an x value, for example -2, the y value there is 4, but the x value of -1, the y value there is +1. It has decreased in values. In other words, this function is coming downwards here towards the left side of the function. But on the right side of the function, it's coming upwards. So here, when we start this side, when x is 1, y is 1. But when x is 2, y is now 4, which is an increase in the y value. So again, that's opposite. Because when x was -2 here, and we went right, y became -1. Y became 1. But when x was 1 here, and we came to the right, y became 4. So this one has an increasing section. Increasing. And that's from the section -infinity all the way to 0. And then it has a decreasing section. From 0 to infinity. So it has both on this particular one. And that point in the middle we call the vertex, which is also a point of inflection, where it changes from increasing to decreasing. So this point right here, 0, 0, is a special point called the vertex, where it changes, in this case, from increasing into decreasing. Alright, this particular one, it's always increasing on the left, even though it starts to increase less and less as you approach 0, it's increasing on the left. So this one has actually the same item as the last one. From -infinity to 0, we increase, and from 0 to infinity, it's actually always increasing. It's actually never going down. My bad. I was thinking if it had the curve, I was thinking if it was doing something like this. Because then you'd have increasing, then decreasing, then increasing. Something like this, where it has actually the 2 points of interest, maximum, minimum is what we call them. But it's not like this, because it doesn't have the actual top and bottom. It just has the middle. I'm going to cross that out so it doesn't confuse you. So this one's always increasing here. Why? Because if you take a value -2 for x, its y is -8. Take the value to the left, to the right of -2, -1, its value is -1. So we've increased in the y values. Take the value -1, go to the right, 0. Well, it's increased in value because y is -1 when x is -1, and y is 0 when x is 0. And same thing here, 1 and 1. We've increased the y value as x has increased. And 2 and 8, we've increased the y value as x has increased. This one is also always increasing. In other words, it's curving upwards. It doesn't have a curve coming down. This is I want to say this is the downward curve here, where it's coming downwards. So this one is always increasing, it's never decreasing. Same thing with this one. Increasing. Alright, the reciprocal function. The reciprocal function is kind of an odd beast, because notice here in the middle, when it comes downwards and all of a sudden it jumps up to here, you would think that would be an increase, because, well, it's coming downwards, well then all it jumps up to here. But how would you write that as an increase? Because that's only a single number, that's 0. That's just x equals 0. So we don't actually write that as an increase at all. This is actually decreasing, and then it jumps up, but then it starts decreasing again. So this is actually always decreasing, is what we say for this particular function. It's a decreasing function. In other words, you can look at this. The y values are always coming downwards, with the exception of when we jump up to here, when x is 0, but x can never actually be 0. That's also what's called a non-continuous function, which has an asymptote. We'll talk about that in a second as well. Alright, next one. This one's always increasing, pointing upwards. Now the sine and the cosine functions are a little bit weird. We'll come back to those ones last. The absolute value function is always increasing. I shouldn't say always increasing. It's increasing from 0 to infinity and decreasing from negative infinity to 0. And then this one at the bottom of this page, this greatest integer function. Notice here that it's kind of an odd item here, because you can see here as x goes up, y does in fact increase. So we're going to call this increasing function, but it increases in a very odd way. It increases one number at a time instead of increasing by fractions like the other functions did. Alright, so looking at the sine and the cosine, there's actually increasing and decreasing parts of this each and every what's called wave. So this particular portion here to here, that would be a decreasing portion. Whereas here, the bottom of the wave to the top of the wave, that would be an increasing function, an increasing portion. So it's actually increasing and decreasing along the entire wave for the entirety of the wave, which the wave is infinite, and the cosine function is the same way. So it decreases from here to here, and it increases from here to here. So it's actually increasing and decreasing along the entire value of the wave. So we're going to have to write that as an equation or expression. Let me see if I can remember a proper way to write that. So increasing from, we're going to have to use a notation with pi in it. Pi is 180 degrees. I don't think we've talked about the wave functions yet. So this is probably not going to make sense to you. I'm thinking I don't want to talk about the increasing and decreasing ranges on this with the functions, because I'm thinking I'm just going to really confuse a lot of you, since we haven't talked about sine and cosine waves. But just keep in mind with these two, they are increasing and decreasing along the wave. Decreasing is when we're going down, increasing is when we're coming up. And we would write that as an expression. I'm thinking I don't want to write the expression right now because it's going to be probably confusing, very confusing. Alright, so this one is always increasing, despite the fact that the increases become less and less as you approach y equals 1. It is always increasing in terms of its values. Okay, what do we have next? Symmetry, odd or even. So remember, for an odd function, you would have f of x is f of x equal to f of negative x? Or is f of x equal to the opposite of f of negative x? So in other words, if you substitute a negative x in, is it the same function just with a negative sign in front of the variable? Or is it the same exact function? That's going to be odd and even. So this one's going to be odd because if you put a negative x in for x, all it does is it changes that into a negative x. So f of x is equal to the opposite of x of negative x. So that's an odd function. Odd. Whereas this one's even. If you put in negative x, it's going to become negative x quantity squared. So that's going to be even because that makes it so it's positive. This one's odd. Why is it odd? Well, if you put in negative x, it becomes the same thing, it just becomes a negative in front. So it's the same equation with just a negative in front of it. This one is actually neither, because if you put in a negative x here, it changes the equation entirely because now it's the opposite inside the square root. So now x has to be negative. So it's not the same thing. So you could also look at this in terms of which axes, or does it have symmetry with the y-axis? That's going to be even. Or does it have symmetry with the origin? That's going to be odd. Now, origin symmetry is not x-axis symmetry. That doesn't mean it flips up and down. Origin symmetry means it rotates like a fan blade. It can rotate along itself, like a fan does. So this one is odd symmetry, and this one is too, because the fan can rotate around. All right, this one again. When we do a negative x in here for this changes it. So the ln of x is not equal to the ln of the opposite of x because it's going to flip it across on the other side. So this one has neither. Where are we at? Reciprocal function. This one would actually have odd symmetry. So if we put in negative x here, it would keep it the same. It would just be opposite signs now in the front. What I'm saying in the front is, I mean, when you put in a negative x here, can that negative x be brought into the front of the expression or the equation here? So if ln of negative x, can that negative be brought to the front of that and still be the same equation? So this one it can, because if you put in negative x, you can bring that in front because the negative can be brought in front of a fraction. But here you could not, because you can't bring that negative outside the ln and keep the equation the same. And same thing with this. You can't bring that negative outside of the square root and keep it the same. It changes it, because when you bring it outside, it becomes an I, not a negative, it's an I. And a similar thing happens here. When you bring that negative in the front, you can't be bringing it in the front. Alright, so here, that negative, if I put a negative in for x here, that's going to switch that to an opposite function, a reciprocal of it. So this is neither as well. Alright, so for sine and cosine are kind of interesting because the cosine function does have symmetry with the even symmetry. And it has symmetry because the cosine of a negative x is the same as its positive x. In other words, the cosine of 2 pi is 1. The cosine of negative 2 pi is 1 as well. But sine is not that way. Because you can see here the cosine of this is 9. If you do here, cosine of 90 is actually the opposite. Or excuse me, sine of 90, or sine of pi over 2, is actually the opposite of sine of negative 90, or negative pi over 2. So sine does not actually have symmetry. It would have odd symmetry. It would have odd symmetry, negative in front. But that is not the case. So like the sine of, actually, is the sine function odd? Because if you put in a negative x, the sine of negative x, is that equal to the opposite of sine of x? I believe that is actually the case. Because the sine of negative 90 is the sine of positive 90. And the sine of positive 270. So this is actually odd. that just tells you right there that sometimes I get confused as well about even versus odd. The best way to talk about it is if you put a negative in for x, can that negative be brought into the front? So is the sign of pi over 2 the opposite? And if you put it as a negative, is it the opposites? And that is the case. So can that negative be brought in the front, in other words, when you put in a negative there? The sign of negative 90 equal to the opposite of the sine of 90. That is the case. Or the sign of negative pi over 2 equal to the opposite of the sine of pi over 2. Alright, so this one here does have y-axis symmetry. So this is an even function. And you can tell here again, because if you put in a negative value for x, it's the same as a positive value, because it's absoluting. Alright, so the greatest integer function, even versus odd. So again, what we're looking at here is the, can you put in a negative x for that, and it will be the opposite? Can the negative be brought into the front? And the answer to that question is, in fact, a yes. Because if you say, like for example, if x was 2, y would be 2. And if the opposite was the case, if x was negative 2, y would be negative 2. They're the opposite values. So that is odd. And then on the last page here, even or odd, this would be neither. Or neither, either nor odd. Alright, last thing is asymptotes. Asymptotes are special values where a graph approaches a number but never actually attains said number. So you have to have a curve for an asymptote to apply. It has to be a curve where the graph actually approaches the number. So these ones don't have asymptotes, these three. Question 4 kind of looks like it has one, but you can't actually continue this downwards because it ends at 0. It actually ends at 0, x equals 0. It doesn't go left of x equals 0. Because you don't do x equals negative 1 here on a regular number coordinate plane. This one is the first one that has an asymptote. So the concept of asymptote is the graph comes down and it approaches this value, but it never actually attains it. You can see here it's approaching it's approaching x equals 0, but it never actually gets to the point where x can equal 0. And y is decreasing and decreasing and decreasing. So that's got an asymptote. Let me use a different color here. I'm going to use purple. A-S-Y-M-P-T-O-T-E. It's got an asymptote at y equals 0. X equals 0. I said it right and I wrote it wrong. Not y equals 0, x equals 0. So x is never going to equal 0 here. And y is going to approach, and it's going to approach 0, but it's never going to equal 0. And y is going to get closer and closer to that. This one has that same asymptote, number 6 does. You can see here that it never actually gets to x equals 0, but it approaches it from either side. From either side it approaches that x equals 0. It's got that asymptote at x equals 0 as well. Alright, so here we got an asymptote at y equals 0. Here and here we don't have any asymptotes. So it does oscillate up and down, but it's not actually approaching any particular number. So here we're approaching y equals 0. We're coming up from y equals 0. We're coming up from y equals 0. So it's approaching and approaching y equals 0 as x becomes more and more negative. So that's why we say it's got an asymptote at y equals 0. Versus this one is not really approaching any particular number. It's just going oscillating back and forth. And the same thing here as well. There's no asymptotes here as well. Same thing here. It comes down, touches at 0, comes back up. It doesn't actually approach y equals 0. It just comes down and touches and then comes up. Same thing here in number 11. Alright, and then number 12, this one has two asymptotes, at y equals 0 and at y equals 1. Y equals 0 and y equals 1. So what that means here is that On the left here, as x becomes more and more negative, the y value gets closer and closer to 0. And on the right here, as x becomes more and more positive, the y value gets closer and closer to 1. Okay. Alright, so domains. So here's discussing the 12 basic functions. Domain. All of the basic functions have domains, sets, the set of real numbers. And I don't like using the keyword all there, but that's kind of what we have it set up there. The reciprocal function y equals 1 over x has a domain of all real numbers. So you can write that as an R like this. I believe that's what we were meant to write here, except x equals 0. The square root functions has a domain of x has to be greater than 0 or equal to 0, 0 comma infinity. The natural logarithm function has a domain of x has to be greater than 0, not including 0. So when I say all of the basic functions have a domain of all real numbers, what I mean is all of them but these three. All of the basic functions except these ones. This one, that one, and that one. So that's what that means when it says all of the basic functions. I could put the word most there. Maybe that would have been a better word to use. Most of the basic functions have a domain set of all real numbers. The same words can be used for the continuity. So I should say most of the basic functions are continuous on their entire domain. So maybe that's the best word to use here instead of all, using the word most. Most of the basic functions are continuous on their entire domain. The greatest integer functions. So this greatest integer function on the last page here, this one here, where it jumps. And we call that we'll just call it the greatest integer function. Greatest integer function has jump continuities at every integer value. And then the other one that has a discontinuity is this one here. What we were talking about with this 1 over x function, when we were saying it skips, that's called a discontinuity. So when it was decreasing and then increased, and it looked like it increased between this and this, but we couldn't figure out what value that was, that's called a discontinuity. So this function is what's called non-continuous, because it comes downwards and then it jumps all the way up. So in other words, it's decreasing, and all of a sudden right here it's supposed to increase, but we can't figure out what value for x it's increasing. In other words, what were the two range? What was the range when x was increasing? Because it's just a single value. It's at x equals 0, where the asymptote happens to be. So that's what's called a discontinuous function, or a non-continuous function. So we call that the reciprocal function here, or 1 over x function. Reciprocal function has an infinite discontinuity at x equals 0. Alright, and it is still continuous because x equals 0 is not in its domain. So Mrs. Missouri wrote this for us because she teaches pre-calc. So it is considered a continuous function because x equals 0 is not part of the domain. So it's not a non-continuous function, it just has discontinuity. At x equals 0, there's a distinction there between those two words, which I usually don't test you on. Alright, so asymptotes. So how many of the functions have a asymptote at x equals 0? So there's the natural logarithm, there's the reciprocal that has x equals 0 asymptote, and that's it. 2 of the basic functions. And the 2 that have the asymptote at x equals 0 are these two: square root function, not square root function, natural logarithm function. Square root function and just ends at 0. Natural logarithm function and reciprocal function. Alright, and the ones that have an asymptote at y equals 0, let's see here, we've got this one, the logistic function. So that's what y equals 0. This one, the exponential function. So two of them also have. Asymptotes at y equals 0. Alright, so here for our reflection. Which of the 12 basic functions are identical except for a horizontal shift? So that's something for you to reflect on from the notes today. Which of these functions could you just move it left or right and it would become another one of the functions? Alright, for your homework, each of us will assign individual assignments, each of us teachers, so I'm not going to put mine there. Good luck. Thank you.